And back with structure and interpretation of computer programs. So let's continue with nested mappings. We can extend the sequence paradigm to include many computations that are commonly expressed using nested loops. Consider this problem. Given a positive integer n, find all ordered pairs of distinct positive integers I and j, where 1 is smaller than j, which is smaller than I, which is smaller or equal to n, such that I plus j is prime. For example, if n is 6, then the pairs are the following. Okay. A natural way to organize this computation is to generate the sequence of all ordered pairs of positive integers less than or equal to n, filter to select those pairs whose sum is prime, and then for each pair ij that passes through the filter, produce the triple ij I plus j. Here is a way to generate the sequence of pairs. For each integer I smaller than n, enumerate the integers j smaller than I, and for each such I and j, generate the pair ij. In terms of sequence operations, we map along the sequence enumerate interval 1n. For each I in this sequence, we map along the sequence, enumerate interval 1, I minus 1, and for each j in this letter sequence, we generate the pair list ij. This gives us a sequence of pairs for each I. Combining all the sequences for all the I by accumulating with append produces the required sequence of pairs. Okay. The combination of mapping and accumulating with append is so common in this sort of program that we will isolate it as a separate procedure. And so here we define flat map. Now filter this sequence of pairs to find those whose sum is prime. The filter predicate is called for each element of the sequence. Its argument is a pair and it must extract the integers from the pair. Thus, the predicate to apply to each element in the sequence is okay. Finally, generate the sequence of results by mapping over the filtered pairs using the following procedure, which constructs a tripole consisting of the two elements of the pair along with their sum. Okay, and here we are just constructing the pair. Combining all these steps yields the complete procedure. Nested mappings are also useful for sequences other than those that enumerate intervals. Suppose we wish to generate all the permutations of a set S, that is, all the ways of ordering the items in the set. For instance, the permutations of 1, 2, 3 are 1, 2, 3, 1, 3, 2, 2, 1, 3, and 2, 3, 1, 3, 1, 2, and 3, 2, 1. Here is a plan for generating the permutations of S. For each item in S, recursively generate the sequence of permutations of S minus X and adjoin X to the front of each one. This yields, for each X in S, the sequence of permutations of S that begin with X. Combining these sequences for all x gives the permutations of S. Of course, the set S minus x is the set of all elements of S excluding x. Notice how this strategy reduces the problem of generating permutations of S to the problem of generating the permutations of sets with fewer elements than S. In the terminal case, we work our way down to the empty list, which represents a set of no elements. For this, we generate list nil, which is a sequence with one item, namely the set with no elements. The remove procedure used in permutations returns all the items in a given sequence except for a given item. This can be expressed as a simple filter. Okay, now we have a couple of exercises. Oh, a solution to the 8 queens puzzle. Okay, this is an exercise. Okay, exercise. Okay, section 2.2.4, example, a picture language. This section presents a simple language for drawing pictures that illustrates the power of data abstraction and closure, and also exploits higher order procedures in an essential way. The language is designed to make it easy to experiment with patterns such as the ones in figure 2.9, which are composed of repeated elements that are shifted and scaled. In this language, the data objects being combined are represented as procedures rather than as list structure. Just as cons, which satisfies the closure property, allowed us to easily build arbitrarily complicated list structure, the operations in this language, which also satisfy the closure property, allows us to easily build arbitrarily complicated patterns. And this reminds me to Escher. The picture language is based on the language Peter Anderson created to construct images like MC Escher square limit woodcut. The woodcut incorporates a repeated scale pattern similar to the arrangements drawn using the square limit procedure in this section. Okay. When we began our study of programming in section 1.1, we emphasized the importance of describing a language by focusing on the language primitives, its means of combination and its means of abstraction. We will follow that framework here. Part of the elegance of this picture language is that there is only one kind of element called painter. A painter draws an image that is shifted and scaled to fit within a designated parallelogram-shaped frame. For example, there is a primitive painter we'll call wave that makes a crude line drawing as shown in figure 2.10. The actual shape of the drawing depends on the frame. All four images in figure 2.10 are produced by images, the same wave painter, but with respect to four different frames. Painters can be more elaborate than this. The primitive painter called Rogers paints a picture of MIT's founder William Barton Rogers, as shown in figure 2.11. Okay, let's look at these figures. This is figure 2.10, images produced by the wave painter with respect to 4 different frames. The frames shown with dotted lines are not part of the images. Let's look at the figure 2.12. Images of William Barton Rogers, founder and first president of MIT, painted with respect to the same 4 frames as in figure 2.10. Okay? So the 4 images in figure 2.11 are drawn with respect to the same 4 frames as the wave images in figure 2.10. To combine images, we use various operations that construct new painters from given painters. For example, the beside operation takes 2 painters and produces a new compound painter that draws the first painter's image in the left half of the frame and the second painter image in the right half of the frame. Similarly, below takes 2 painters and produces a compound painter that draws the first painter's image below the second painter's image. For some operations, transform a single painter to produce a new painter. For example, flip vert takes a painter and produces a painter that draws its image upside down, and flip orange produces a painter that draws the original painter's image left to right reversed. Figure 2.12 shows the drawing of a painter called Wave 4 that is built up in 2 stages starting from wave. And so we basically with a single painter wave we can create complex figures. In building up complex image in this manner, we are exploiting the fact that painters are closed under the language's means of combination. The beside or below of 2 painters is itself a painter. Therefore, we can use it as an element in making more complex painters. As with building up list structure using cons, the closure of our data under the means of combination is crucial to the ability to create complex structures while using only a few operations. Okay, so far so good. Once we can combine painters, we would like to be able to abstract typical patterns of combining painters. We will implement the painter operations as a scheme procedure. This means that we don't need a special abstraction mechanism in the picture language. Since the means of combination are ordinary scheme procedures, we automatically have the capability to do anything with painter operations that we can do with procedures. For example, we can abstract the pattern in wave 4 as and define wave 4 as an instance of this pattern. Recursive plans for right split and corner split. We can also define recursive operations. Here's one that makes painters split and branch towards the right, as shown in figure 2.13 and figure 2.14. We can produce balanced patterns by branching upwards as well as towards the right. Okay. By placing 4 copies of a corner split appropriately, we obtain a pattern called square limit, whose application to Wave and Rogers is shown in figure 2.9, the one we saw before. Okay? Higher order operations. In addition to abstracting patterns of combining painters, we can work at a higher level, abstracting patterns of combining painter operations. That is, we can view the painter operations as elements to manipulate and can write means of combination for these elements. Procedures that take painter operations as arguments and create new painter operations. For example, flipped pairs and square limit each arrange 4 copies of a painter's image in a square pattern. They differ only um, in how they orient the copies. One way to abstract this pattern of painter combination is with the following procedure, which takes for one argument painter operations and produces a painter operation that transforms a given painter with those 4 operations and arranges the results in a square. TLTR, BR are the transformations to apply to the top left copy, the top right copy, the bottom left copy, and the bottom right copy, respectively. Okay, then flip pairs can be defined in terms of square of 4 as follows. And square limit can be expressed as this. Okay, exercise, frames. Before we can show how to implement painters and their means of combination, we must first consider frames. A frame can be described by 3 vectors, an origin vector and 2 edge vectors. Okay? That's basically how we defined rectangles in one of the previous exercises. Where we basically, to describe a rectangle, we decided to define the bottom left corner and then the sides and the height of the rectangle. Okay, so if the origin vector specifies the offset of the frame's origin from some absolute origin in the plane, and the edge vectors specify the offsets of the frame's corners from its origin. If the edges are perpendicular, the frame will be rectangular, otherwise the frame will be a more general parallelogram. Figure 2.15 shows a frame and its associated vectors. In accordance with data abstraction, we need not to be specific yet about how frames are represented, other than to say that there is a constructor makeFrame which takes 3 vectors and produces a frame, and 3 corresponding selectors: origin frame, edge 1 frame, and edge 2 frame. We will use coordinates in the unit square so that x and y are included in the interval 0, 1 to specify images. With each frame, we associate a frame coordinate map which will be used to shift and scale images to fit the frame. The map transforms the unit square into the frame by mapping the vector v xy to the vector sum. Okay? For example, 0, 0 is mapped to the origin of the frame, 1, 1 to the vertex diagonally opposite to the origin, and 0.5, 0.5 to the center of the frame. We can create a frame's coordinate map with the following procedure. Okay. Observe that applying frame chord map to a frame returns a procedure that, given a vector, returns a vector. If the argument vector is in the unit square, the result vector will be in the frame. Okay? Exercises. Painters. A painter is represented as a procedure that, given a frame as argument, draws a particular image shifted and scaled to fit the frame. That is to say, if P is a painter and F is a frame, then we produce P's image in F by calling P with F as argument. The details of how primitive painters are implemented depend on the particular characteristics of the graphics system and the type of image to be drawn. For instance, suppose we have a procedure draw a line that draws a line on the screen between two specified points. Then we can create painters for line drawings, such as the wave painter in figure 2.10 from lists of line segments as follows. The segments are given using coordinates with respect to the unit square. For each segment in the list, the painter transforms the segment endpoints with the frame coordinate map and draws a line between the transformed points. Representing painters as procedures erects a powerful abstraction barrier in the picture language. We can create and intermix all sorts of primitive painters based on a variety of graphics capabilities. The details of their implementation do not matter. Any procedure can serve as a painter provided that it takes a frame as argument and draws something scaled to fit the frame. Okay, couple of exercises as usual. Transforming and combining painters. An operation on painters works by creating a painter that invokes the original painters with respect to frames derived from the argument frame. Thus, for example, flip vert doesn't have to know how a painter works in order to flip it. It just has to know how to turn a frame upside down. The flipped painter just uses the original painter but in the inverted frame. Painter operations are based on the procedure transform painter, which takes as arguments a painter and information on how to transform a frame and produces a new painter. The transformed painter, when called on a frame, transforms the frame and calls the original painter on the transformed frame. The arguments to transform painter are points, represented as vectors, that specify the corners of the new frame. When mapped into the frame, the first point specifies the new frame's origin and the other two specify the ends of its edge vectors. Thus, arguments within the unit square specify a frame contained within the original frame. Okay. Using Transform Painter, we can easily define new transformations. For example, we can define a painter that shrinks its image to the upper right quarter of the frame it is given. Other transformations rotate images counterclockwise by 90 degrees, or squash images towards the center of the frame. Frame transformation is also the key to defining means of combining two or more painters. The beside procedure, for example, takes two painters, transforms them to paint in the left and right halves of an argument frame respectively, and produces a new compound painter. When the compound painter is given a frame, it calls the first transform painter to paint in the left half of the frame and calls the second transform painter to paint in the right half of the frame. Observe how the painter data abstraction, and in particular the representation of painters as procedures, makes beside easy to implement. The B-side procedure need not to know anything about the details of the component painters other than that each painter will draw something in its designated frame. Levels of language for robust design. The picture language exercises some of the critical ideas we have introduced about abstraction with procedures and data. The fundamental data abstractions, painters, are implemented using procedural representations, which enables the language to handle different basic drawing capabilities in a uniform way. The means of combination satisfy the closure property, which permits us to easily build up complex designs. Finally, all the tools for abstracting procedures are available to us for abstracting means of combination for painters. We have also obtained a glimpse of another crucial idea about languages and program design. This is the approach of stratified design, the notion that a complex system should be structured as a sequence of levels that are described using a sequence of languages. Each level is constructed by combining parts that are regarded as primitive at that level, and the parts constructed at each level are used as primitives at the next level. The language used at each level of a stratified design has primitives, means of combination and means of abstraction appropriate to that level of detail. Stratified design pervades the engineering of complex systems. For example, in computer engineering, resistors and transistors are combined and described using a language of analog circuits to produce parts such as AND gates and OR gates, which form the primitives of a language for digital circuit design. These parts are combined to build processors, bus structures, and memory systems, which are in turn combined to form computers using languages appropriate to computer architecture. Computers are combined to form distributed systems using languages appropriate for describing network interconnections and so on. As a tiny example of stratification, our picture language uses primitive elements, primitive painters, that are created using a language that specifies points and lines to provide the lists of line segments for segments painter, or the shading details for a painter like Rogers. The bulk of our description of the picture language focused on combining these primitives using geometric combiners such as beside and below. We also worked at higher level regarding beside and below as primitives to be manipulated in a language whose operations, such as a square of 4, capture common patterns of combining geometric combiners. Stratified design helps make programs robust, that is, it makes it likely that small changes in a specification will require correspondingly small changes in the program. For instance, suppose we wanted to change the image based on wave shown in figure 2.9. We could work at the lowest level to change the detailed appearance of the wave element. We could work at the middle level to change the way corner split replicates the wave, and we could work at the highest level to change how square limit arranges the 4 copies of the corner. In general, each level of a stratified design provides a different vocabulary for expressing the characteristics of the system and a different kind of ability to change it. Very interesting this part. Nothing new, but it makes you think about how you build programs. The concept of stratification that in a sense is similar to the concept of modularity that was introduced in the first chapter it's very interesting. So I think we can stop here, and in the next video we will continue with symbolic data, the section 2.3. Let me see. Okay, symbolic data. And then we will have also multiple representations for abstract data and also systems with generic operations. Okay, see you in the next video. Ciao, ciao.